Hello and welcome back to another LeetCode video. So today we're going to be doing the problem of the day for June 18th. It's actually another hard problem, kind of interesting. I think we had like 3 or 4 hard problems in a row for the problem of the day, which is pretty rare. But it's going to be 2328, number of increasing paths in the grid. You're given an n by n matrix grid where you can move from any cell to all adjacent cells in all 4 directions. Return the number of strictly increasing paths in the grid such that you can start from any cell in the grid and end at any cell. Since the number may be very large, return it modulo 10 to the 9 plus 7. 2 paths are considered different if they do not have the same sequence of visited cells. So let's actually look at this example here. Okay. And so what they are saying here is like this one and this one are different because they are in different rows and columns. So as long as you're visiting two different elements can have the same number, but you have to treat that as different paths. And so what are all the paths? Well, all the one length paths that are strictly increasing are 1, then this other 1, and we have this 1, 3, then we have this 3, 4. And by the way, so we do have 2 more paths that are 1 length, which is the 3 and the 4. So every single cell is going to be a 1 length path. So that, then we have this 1, 3, 4, that's the longest path. Okay, and so that's all the paths, I believe. Did I miss one? I think I did. Let's see here. 1, 3, 4, 1, 3. Oh yeah, so we also have this one right here, 1, 4. So I forgot that one. But that is all the paths. That's 8 paths. So now we need to figure out how to actually calculate these paths and what these paths actually mean. And it's actually going to be pretty straightforward, to be honest. Like, even though this is a hard problem, it's not going to be that bad. So let's actually redraw this again. And think of what like a path means. So there's 2 ways to do this problem, and I'm going to do it kind of like the way that makes a little bit more sense, and I'm going to kind of show you. The code is actually pretty identical, but it means 2 different things for both ways of doing it. But I first did it one way, but it's kind of a little bit counterintuitive, so I'm going to show it the more intuitive way. So let's actually think of, for example, we're at this cell. What we can do actually is for every cell, we can just write all the paths that end with that cell and ask us what that means. And so we're going to have a memoization where we're just going to ask us, okay, let's take every path that ends at the current cell we're at, and then we're going to iterate through every single cell and do that, right? So we're going to check here, what's every path that ends here, here, what's every path that ends here with here. And so you can kind of see from doing it that way, you're going to get unique like paths, right? But we don't actually have to record all these paths. We just need the number. And so let's try to do that then. Because yeah, like, oh yeah, let's just actually go through it and then I'll show you how it works. So maybe we should also do, no, this is fine. Actually, let's change this 1 to a 2 maybe. And then that way it would be a little bit more intuitive because then we know like which thing is which, right? So something like that. Okay. So let's start with this 1. So what's every path that ends with a 1? Well, the way we're going to do it is pretty straightforward. So we are going to, from this cell, if the cell ends with a 1, we just have to be going backwards then, right? So we have to be going to cells that are less than the 1. So it's going to be, if you think about it, every path that ends with a 1, the number of paths that end with a 1 is going to be the number of paths that don't, right? So it's the number of paths that end with 1 less than a 1, and then we can just plop a 1 on to the end, right? So for example, and I'll show you what this means once we do a later example, that don't end with a 1, that 1 is greater than. And this is like that 1 is, you know, the cell after. I'll just write it like that, and I'll show you what that means. So what I mean by the cell after, meaning like it's going to be a cell that it's going to be the path from a cell that would go to 1. And so since it has to be strictly increasing, we can't go from anywhere to 1. So in this case, actually that would be 0 paths, right? So for this, there are 0 paths that would go to 1. that one would end with, except for we do have to initialize this to, let's actually delete this so we have more space. And we're just going to store this over here. So the number of paths that end with this 1 here is going to be just this, because there are no paths like when we recurse, we're going to recurse to paths that are smaller than this one that are directly, you know, that are a direct neighbor, but there are no paths for 1. And so for 1, but like I said, there is the base case where you do have, it's not really a base case, but for every path that ends with whatever cell you're at, you're always going to have just the cell itself. Okay, so now let's go to 2, and it's going to make a little bit more sense. So now that we're at 2, we need to go to every cell that can go into 2, right? So 1 can go into 2 because 2 is greater than 1. And then we need to take the paths from that cell, and then we need to figure out how many that is, and we can just plop a 2 on the end. And so let's do that. So when we go to 1 here, right, we're going to recurse down to this 1, and we're going to say, okay, what are the paths that 1 can end at? Well, we already actually calculated that. So it's just this. And so what we can do is we can say, okay, for every path that ends with a 1, let's just plop a 2 on the end. That's a path, right? And we can always do that because 2 is greater than that cell. Okay? So that's going to be that. And now remember, there is also the path that just has the node itself. Okay, now let's go to 3. And same thing, we're going to go to every single node that we can go down into that's smaller than 3. So that's only this 1 node. And so we're going to say, okay, what are the paths that end with a 1? Well, it's just the 1. And so once again, we're going to plop the 3 onto the end. That's a path. And then we have the base case of 3. Okay. Now let's go to 4. And so from 4, we can go to 2 ways. We can go to 3. So let's go to 3 first. And so what are all the paths that end with 3? Well, we have that calculated. So it's going to be 1, 3, and 3. Right? And we're just going to add the 4 to the end of those because that's a path and that's a path. Right? Now let's go to 2. And what are all the paths that end with 2? Well, it's going to be 1, 2. I'm going to leave some space here. And it's going to be 2 as well. And now we're just going to put the 4 on the end. And then we do also, like I said, we have the case where we just have the 4. And so if you look at this, this is actually all the possible paths we can make. So this is 9 total paths. Maybe I skipped one, but that's kind of how we do it. So let's write our recursive algorithm here. And it's actually pretty straightforward. So let's make this a little smaller. So we are going to iterate through the matrix and start, so we're going to iterate through every matrix, and we're going to go to every single, point in the matrix, right? So every single row column combination, and go to every row column combination. And that's going to symbolize that our path ends with that with that exact number. So we're going to do that, and call DFS. Let's just call this DFS on it. Okay, so that's step 1. Now we need to, so this is step 1. Now in the DFS, we will travel to all cells lower than it and add all those paths to the result, right? So for example, when we go from this 3 to the 1, we don't actually need to store these paths. We just need to know how many there are. So if we go to this from this 3 to the 1, then the 1 only has 1 path. That means 3 paths that end with a 3 will have that path, right? So this 1, 3 right here. And then we also need to add 1. So we're gonna try to traverse from every cell to every cell that's lower. And then we are also going to, so the number, so let's do that and add those paths to the result. So we can write that over here. So the number of paths ending with a cell is the sum of the DFS from the cell in all 4 directions to cells lower than it. +1, right? Because we have that extra +1. I think. Okay, there we go. So yeah, so we have to try to go to every single cell we can. Now the cells have to be lower and they also have to be in bounds. And then we have that +1 because we also have this case, right, where we just have the number by itself. So we are going to have a loop that's going to start with every single one of these. We're going to have a visited hash map, and then we are going to DFS down to every single row and column that's less than like where we're at, and then we're going to recursively get those. And the thing to remember is, like, let's say we get to this 3. It doesn't matter how many times, like, from where we got to the 3, because the number of paths that end with a 3 is the same no matter how we got there. So if we got to this 3 from this 4, or let's say we had a 5 or something that got to the 3, the number in here, the number that this should return is always going to be the same. So that's why we can use memoization, because the path, if you think about it, the path doesn't actually matter. All we're concerned about is how many paths end with 3. And so the way to know, like for 4, how many paths end with 4 would be the number of paths that end with 2 plus the number of paths that end with 3 plus 1. So this isn't actually 2 and 3. This is the number of paths that end with 2, the number of paths that end with 3, and then this is just this one is just the 1. Okay, so hopefully that makes sense. We're gonna go through the matrix and then we're gonna DFS down, and I'll show you the way I did it. That afterwards, that is a little bit less intuitive, but it's actually pretty much. It's like one line of code difference. Okay, and the nice thing about this is that this will be m by n, because we are only going to we only have to calculate the DFS for each of these one time. Now that we recognize that it doesn't actually matter, like we made our code in a way that it doesn't actually matter how we got to each of these values. All we're concerned about is the number of paths that end with each of these values. Okay, so we're going to iterate through the matrix, go to every single row, call DFS. In the DFS, we will travel to all cells lower than it and add all those paths. And then recursively, like let's say we try to go to this 2 and this 3, these can travel to other paths, and then they will do the same thing, right? So the number of paths in 2, well, actually, this would be stored after the first time. So once we calculate this 2, it wouldn't actually recurse further. It would already be stored. But yeah, if you want to actually calculate it again, then it would recurse down to the paths that are lower than it. But it's pretty straightforward once you recognize that all the paths ending with some node are just all the paths ending with the node next to it, and you just plop that node onto the end of them. I think there are some other problems in LeetCode like that, where you're trying to find like the longest path or something like that. And it's the same kind of situation, but except this one's a little bit more difficult, because figuring out the memoization and how this actually works is a little bit more difficult with all these paths. Longest path seems a little bit more intuitive, but it's pretty much the same problem. Okay, so let's code it up. So what we're going to need is we're going to need rows and columns equals length grid 0. Okay, now we are going to need directions as always. This is pretty much the same thing as in all my videos. So we're going to have 1 0 0 1 -1 0 and 0 -1. Oops. Okay, so we have the directions, we have the rows and columns, we need the visited set, same as always. Now we're actually going to do the DFS here, row, column. And so we don't really, our only base case here is if our row and column is in visited. We don't really have a, once we reached whatever row and column, we need to stop. So we're going to just keep going. We need to always check the 4 rows and columns, no matter like where we're at. Okay, so if row, column, in visited, return visited column. Okay, that's a little annoying. Okay, now we are going to make our result here equals to 1, because remember that's like the initial case, because the DFS from any single point can be just itself. So we're going to make it 1, and then we're going to add more on top of that. So for direction in directions and row and call equals row plus direction 0. Then we have column plus direction 1 Okay, so that's that. Now we need to actually check if they are valid, and if they're valid, then we will go to those. So if 0 and row is less than rows, and so this is just to make sure that n rows in bounds. Now we have to do the same thing for column, call, and columns, and grid n row n call is less than the grid of the cell we're currently at, right? We're going down, so we have to be strictly going down to cells that are smaller than that cell, because that means that we can plop whatever number we have to the paths of those cells. They have to be smaller. Okay, now we will do res plus equals DFS of row and call. Okay, so if it's valid, we can add those. Then we just do this equals res, return res. I think we can actually mod it by this big number here. So let's do that. So it's saying that like there's results going to be really big. So let's actually use this big number to make our results smaller. And we should be able to do this because we are just adding numbers. We're not like dividing or anything. So we should be able to just do that here. Yeah, that's fine. Okay. Now we need to, so remember, we need to loop through this actually whole matrix and use all of these cells as a, we need to call DFS from all those cells because we need to try to have a result that ends with all of these different cells. Okay, so that's pretty straightforward. We can have a result here. Okay, and then we can do the mod here. So actually we could just do this as well. I think this shouldn't give us any issues, but we'll see. So this should return, we can mod it one more time just in case, but it doesn't really matter. Let's see. We can do this as many times as we want. Okay. So the funny thing, okay, so I will say what I did in the first time. So when I did this originally, what I did is I showed like how to do it with cells that actually end with something. So what I originally did was I said, instead of doing it with cells that end with a number, let's actually do it with cells that start with a number. So for example, if we're at this one, let's figure out like how many paths actually start with this number 1. And it's kind of the same thing. So for paths that start with this number 1, you would just go to cells that are greater than itself, and then you would figure out how many paths are there, and then you can actually plop it in front of those. I just think it's a little bit less intuitive to think about. And so actually, if you do this, funnily enough, this code still works because now we're going strictly upwards. And so either one of these still works, and they're around the same runtime. I mean, they should be the same, right? So yeah. Okay. And so let's do the time and space here. So for the time, we are iterating through the entire grid, right? And then this directions, there's only 4, so that's constant. So that's going to be m by n, where those are the directions of the grid, because since we have the memoization, we're only going to actually calculate each of these states one time. And so that's just going to be m by n. And for space, that's going to be m by n as well, because we have the memoization grid, which can be at most m by n elements, because that's how many we have. Okay, so that's all for this problem. Hopefully you liked it, and if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.